All right. I will begin. Hem. 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 Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this class. In the name of our Lord Jesus. Amen. So, fun fact. M squared minus n squared is m plus n times m minus n. Yeah. Attendance. It's not time for attendance yet. Nice try, though. But now that I've been reminded, it's helpful. Let's see here. Let's see here. Ahem. So, win some, you lose some, I guess. Let's see here. So,
I did that. He said no.
Oh, really?
Yes.
Because if that's equal to 1, then those are both factors. Well, okay, fine. He has a different. It's fine. Never mind. It depends on if you've already proved that the only way to get 1 as a product of integers is 1 and 1 and minus 1 and minus 1. Then if you already know that, that algebra leads to a proof. But he's looking for you guys to give a different proof. It's fine. It's fine. So my comment was irrelevant. That's funny. Okay, so proposition. For those of you who don't know what I'm talking about, it doesn't matter. Let's see here. Proposition 7.45. Suppose U, a subset of Rn, is open and connected. Then the following are equivalent. Number 1, F is conservative on U, which means F is equal to the gradient of some function F on U. Number 2, F is path independent on U. All right. Number 3, the integral around any loop of the vector field is equal to 0 for any loop in U. And then 4, if we add n equals 3 as precondition, gradient of f, curl of f equal to 0 on U. I suppose I could say more. I could say if you have n equals to 2 as, precondition. In other words, I'm supposing, in the two-dimensional context, if you had f equals to p comma q with partial q, partial x equal to partial p, partial y on U. That's the two-dimensional version of item 4, which hopefully I will give you some evidence for by the end of today. So this is proposition 7.4.5, and I'd like to try to prove a fair amount of that today. I've already proved for you, so again, 2 if and only if 3 essentially follows from the fact, so 2 path independent, we can go from, from point 1 to point 2, C1, C2, versus taking a loop, right? Taking a loop, we can look at the loop as, for a given loop, we can divide it up into a upper piece and a downer piece. So the loop is really the union of the upper well, C down, let's say. Sorry, I'll get right eventually. C up union with minus C down, because it's the opposite direction, right? And so the fact that you can either start with two paths and form a loop, or that you can take a loop and split it into two paths. In the calculation I wrote on the last board, the last class, suffices to prove that 2 is true if and only if 3 is true. All right. Why 4 is related to any of this, I'll have to explain eventually in here. We may not even get to why 4 is equivalent and on this list today. All right. I mean, we have part of 4 already, right? What do we have? I can do part of the proof here for why is 4 connected to 1. If 1 is true, then what? F is equal to the gradient of little f, right? On U. Thus, the curl of f is the curl of the gradient of little f, which is equal to 0, because that's an identity that we know. So this shows you that 1 implies 4, right? But why should 4 imply 1, right? Why should these be equivalent? It's not at all obvious at the moment why that should be anyway, why we should be able to reverse that arrow. Okay? So what I want to work on here mostly is, I drew it in red last time, but I want to work on why is it that path independence implies that. I mean, I would remind you that we have already proved that 2 implies 1 last time. How do we do that? Oh, I'm sorry, I'm an idiot. The whole point is that you got to be careful which comes first, right? If it's raining, the ground is wet, but if the ground is wet, does that mean it's raining? No, people have hoses, right? So 1 implies 2. That was, if f is equal to the gradient of little f, then if we look at the integral from C1 of f dot dr is going to be equal to the integral of C2 of f dot dr, since f of q minus f of p is equal to both of these. Right? So I'm assuming that C1 and C2 are two paths in U that connect the point P to the point Q, right? So the fact that the value of the line integral depends only on the endpoints if it's conservative, right, because of the fundamental theorem of calculus for line integrals, means that if we have a potential function for f, then we get equality of these different line integrals for curve 1 and curve 2 because of the fundamental theorem of calculus for line integrals, right? These both are just equal to that, right? But what's much less obvious is why 2 implies 1, and that's what I want to work on here for a little bit, right? So we're going to assume that f is path independent on U, where U is an open connected set. And I'm just going to do it in the n equals 2 case, because if we can understand the argument for n equals 2, it's going to work just as well for higher dimension. So for simplicity, for sake of brevity, take n equals to 2. And also just it makes it a little bit easier for us to look at. And maybe here's a picture. I don't know what it looks like exactly, but it's an open connected set. It could look like all kinds of things. I don't know. There could be some like a tail. Looks like I'm drawing a digestive tract or something here. It's here. I mean, the point is that it's open. So it's open. It doesn't have, all the edges are fuzzy. All right. It's connected. That means that if you take any 2 points in the set, right, like this point and that point, there's some path that connects those 2 points in the set. That's what connected means. It means you can draw a line or a curve inside the set which connects any 2 points. Okay, technically that's path connected, but path connected and connected are the same in our context. So, all right, so that's what our assumption is. We've got a path independent. So what are we assuming? What's this mean? This means the integral over C1 of f dot dr, right, is equal to the integral over C2 of f dot dr, provided what? C1 and C2 fit inside U with same terminal points. So they start and end at the same point, okay, guys? So what I need to do, here's the way you, what's our goal? I'm trying to show 2 implies 1. What does it take to affirm the truth of 1? We have to find a little f, right, a potential function whose gradient is the given vector field. So let's introduce a little bit more notation. We're going to set f as usual to be p comma q, all right? And we're going to pick a point. Let's pick this point, x naught, y naught. Pick a point. In U, all right? There's, I mean, you can pick a point, right? And then what I want to do is describe to you over here at x comma y, I want to tell you what I'm going to construct define f little f of xy as being the integral from x naught to y naught to xy of f dot dr. Or if you like, this is the integral from x naught to y naught to xy of p dx plus q dy in the other notation. Why is this reasonable? What does that even mean, the integral from a point to a point? C is any path in U going from x naught, y naught to xy. Now, when you're defining a function, you may recall Dr. Sprano's Calculus 1. First question, first test, what's a function? Function could have as many values as you like. Put in 1 input, you get 3 outputs. It's function. No, 1 input leads to 1 output, right? So it's single valued. Why is this function f of xy single valued? It's single valued because it doesn't matter what my choice is for C, right? There's lots of different choices. Doesn't matter what those choices are. We're assuming path independence, which means all of those choices lead to the same value, namely that integral, that line integral. All right? So this is a reasonable definition. So what do I need to show? What's my goal? So our goal is to show that the gradient of this construction, this gradient of this f, so constructed, is equal to p comma q. That's what if we can show that, our job is done. We've proved that this is in fact the potential function. So let's start with looking at some path like this. What we're going to do is we'll let the curve start here, go up to like here, and go a little bit past it, something like that. Something like this. No, that's not what I want. Sorry. Oh, no. Oh. Did I draw a picture in my notes? I didn't draw a picture, did I? Where's the stupid thing? My laziness has come back to me now. Let's see here. I called it curses. I've done a three-dimensional proof in the notes. Well, that's annoying. So I start at my point, and I call it A in the notes. I think it's fine. So we can call this curve. It doesn't matter what we call it. So let's see here. The point is, we'll call this C1. And then over here, I'll call this C2, right? And so, stink. All right. Let's try to calculate. What I want to do is I want to calculate partial f, partial x. That's what I'm trying to calculate, partial f, partial x. So I think that's the wrong path at the moment. This will do partial f, partial y. I'll tell you what I'll do that. Partial f, partial y. At the point x comma y, I suppose. So that would be the integral so I've got some mental block at the moment, guys. I'll get over it, though. Partial f, partial y. We have the integral along C1 of f dot dr plus the integral along C2 of f dot dr. Right. Okay, now we're good. We're good. So my question to you is this C2 path, right? Well, rather the C1 path. If we change y, you know, if you move this point up and down here, right? Excuse me. If we vary, okay, here's the question. If we vary the point x comma y, holding x fixed, right? Think about this. Vary the point x comma y, holding x fixed. Notice C1 does not change, right? So what can we say about, I'm sorry, there's a giant big problem with this equation. It's not true. So let me fix it. Partial y of all of this, okay? Because that together is the integral over C1 plus the integral over C2. I mean, technically speaking, I should let C2 end at the point xy, all right? But, okay, so you can see that because of that sentence I wrote right under there, because the integral over C1 has no dependence on y whatsoever, right? As I move that point x and y up and down, it doesn't change my initial path C1 one iota. So the partial derivative with respect to y of the first line integral is just what? This is 0. So really, I just have to calculate the integral along C2. Can you tell me what the parameterization is of C2? Let's say R2 of t is what? Well, the x component is x, right? What's the y component? I guess I need to know this joining point for the y component, right? What's this point here? Well, it's x comma, let's say y1, right? So it should be something like y1 plus what? Plus t times what? Y minus y1 maybe? That parameterization of C2 would put the point x comma y where? At time 1, right? So this has dx equals to 0. It has dy equals to y minus y1 times dt. Maybe that's, oh, stink. I've chose poorly. Actually, what I want to do, guys, I've done badly here. Let me choose a different parameterization that'll be easier for us to think about. What if I just do, let's say y plus t, right? That'd be smarter. And this would be, I need what? I need y minus y1 less than or equal to t less than or equal to, I don't know. Well, if I want it to end at y, I can just put 0 there, I suppose. Right? That would parameterize the vertical line segment that goes from the point y minus. Oh. Yeah, it goes from the point. I can't do math. So what I need, if I want to get y1 to be the lower point, what should I put here? Other way around, right? y1 minus y. Because when I add this, when I put that into t, I get y1 plus y minus y, which is just y1 again. All right, I'm sorry. I'm taking forever to argue this here. But the point is, we'd have partial y of the integral, and let's see here, what are my bounds? Apparently y1 minus y to 0, right? Of, oh, I'm sorry, I'm working myself into a corner here. This is dumb. Yeah?
Why does t have to be smaller than or equal to?
Because of the way I parameterized the line, I suppose. Because if 0 is the end point, it's just a consequence of my... If you don't mind, I'm going to do a little surgery here. There we go. No! Lost its tail. All right, so the point is here, partial f, partial y of the point x comma y should be partial y of... And now, so I've just worked out for this integral, we have explicitly the integral from y1 minus y to 0. And so in this, what's the dr, so to speak? dr2 vector looks like what? It looks like 0 comma dt, right? If you'll allow me that heuristic here, which is convenient. So that dr2, the one that I put here, it completely ignores p, right? And it just picks up q. So we have q, which is a function of what? It's a function of, so a function of x comma y plus t dt. Right? But then by properties of, integration, that's what? This is partial y of, well, let me just get through it. That's what? That's, what is this? Do you want me to make, I'll make another step. This is minus the integral from 0 to y1 minus y, right? But what happens when you, and so this is we're differentiating with respect to y. The upper bound is what? Remember fundamental theorem of calculus part 1? What did it say? If you differentiate an integral with a variable bound, you just get the integrand back again. In this case, it's a little bit funny because we get q of x is a constant that rides along. And we plug in the upper integrand, which is y plus y1 minus y, right? And then we're supposed to multiply by the derivative, in this case, y1 minus y. There's that minus. So that minus cancels this minus, and we just get q of x comma, looks like y1. Oh, I've messed the proof up somehow. I'm sorry, guys. I should get x comma y there, not x comma y1. Well, about 1 of every 2 years I try to prove this thing, I mess it up. So apparently you're on an odd year or an even year. I don't know, depending on how you number it. This is essentially the proof. You look at a path, then you look at a vertical path. By looking at that vertical path and labeling points more carefully, when you study the partial derivative of that integral, you'll just get the q, right? Which is half of what we need. We need partial f partial y is equal to q, and we need partial f partial x is equal to p, right? So my apologies, it hasn't quite worked out right. It's a question of interpretation and labeling. I probably should invent a third point and think harder about what I'm varying. So I'm so sorry, guys. But I think we should move on rather than me trying to fix it. My pride can take a hit. It's fine. I'll be okay. The point is you understand the theorem. That's more important, actually, than the proof at the moment. So we can, in fact, construct... So anyway, errors on my part aside, we can show that partial f partial x is p, and partial f partial y is q. And in so doing, you have proved that the gradient of little f is equal to the given vector field f. And this argument I'm trying to sketch still works in 3 dimensions, because you can still take a little path that approaches the point you're interested in, and then just becomes purely in the x direction, or purely in the y direction, or purely in the z direction, close to the point. And then by this argument that I've almost given you, you can prove that the gradient of the so constructed function is in fact the vector field. So here's an example of this. If we take v of x, y, z integral from your reference point x naught, y naught, z naught to the point x, y, z of the electric field dot dr. Do you recognize this formula? Is there a minus? I'm trying to remember. How is the electric field related to the voltage? For those of you who are in 232. Did you learn this? The electric field is minus the gradient of the voltage function? Yeah? No? Am I just talking to myself? He doesn't write it that way. What's he use for voltage? What letter? What? V? It's more like this. Oh.
That's not, like, he doesn't write it as, like, the gradient.
Oh, so he writes it, E is like partial V, partial X, I, like this? Or just he doesn't think of it this way at all?
He wrote that maybe once.
Okay.
I think that's the way the book describes it.
Yeah.
Doesn't use gradient, but either way, that's
Mm. Sad. All right, well, I think there's a minus there, though. So I want to say I'm supposed to put a minus here. Here, let me just check real quick. The electric field, suppose you have the Coulomb field, which is what? It's kq over, r squared r hat. Well, I guess for us that would be rho squared rho hat. And so if I wanted to, suppose I take the, x naught, y naught, z naught to be infinity, so to speak, and then just consider my curve to be the radial path inward, the integral of E dot dr along this curve would be the integral of kq rho hat over rho squared. My dr would be, so dr is like this. So dr would actually be equal to minus rho hat d rho. And that, so that gives me kq integral of d rho over rho squared. There's a minus out here now. And this is going, I need to come up with, like, what rho should the point we're thinking about be? Let's call this rho naught. Oh, I shouldn't do that. Rho, I don't know, 1. So we're going to the point rho 1. The, oh, goodness gracious, from infinity to the point rho 1. And so that would be, what's the integral of 1 over rho squared? Minus 1 over rho. So that minus compensates this minus and gives me 1 over rho, evaluated from, rho 1 to infinity. But of course, that gives us kq over rho 1 minus 0. I'm writing infinity, but of course, that's a notation for a limit. And so there you go. The voltage at rho 1 is kq over rho 1. Perhaps you recognize this if you've had Physics 232. This is the voltage at rho equal to rho 1. In other words, the distance rho 1 from the origin for the point charge at the origin, assuming the voltage is 0 at infinity. So you can see that, yes, I did remember correctly, or did I? Oh, no, I don't need the minus, do I? So I was, no minus here. I was debating whether or not I'm supposed to put a minus there. No minus. Yeah. Anyway, here's a rather complicated example, in some sense, from Physics 232. It's actually not complicated, but it seems complicated because I've used infinity as a reference point, which is, nah. Anyway, I'd rather not get into that. I don't know why I started this. My apologies. Oh. All right. So that is about 60% of the proof that 2 implies 1. We're gonna move on here. Let's see here. Example. Let's see here. Suppose we want to calculate the integral over the unit circle. Well, not the unit circle. Let's say x squared plus y squared equals to r squared of, let's look at minus y dx plus x dy divided by x squared plus y squared. So what does that notation mean? And it's too small on the board, but I'm going to say counterclockwise, okay? So we could, in my other notation, this typically would look like the integral of, minus y over x squared plus y squared, comma, x over x squared plus y squared, dot, dr over the C1, or let's just say C, where C is counterclockwise oriented circle, radius r, centered at origin. All right. That's a lot of writing. So let's calculate this. And so if we calculate this, if this integral is non-zero, what does that mean? What can you tell me about this vector field f? I'm going to call this thing f. Would that, it's not conservative, right? Because it has an integral around a loop, which is non-zero. So let's work it out. Another example. So parameterize C, how do we do it? X equals to, how about r cosine t? Y equals to r sine t. 0 less than or equal to t less than or equal to 2 pi. I mean, if you wanted to use theta instead of t, I wouldn't balk. Be like, that's cool. I mean, that is what t is. T is the standard angle here. That's its geometric meaning. You wouldn't be wrong. But I'm using t. So dx is minus r sine t, and dy is r cosine t. I forgot something very important. This is non-negotiable. It's got to be there. Yeah, the dt. Oh man, this marker's sad. So the dt. And all right, so when we calculate this, x squared plus y squared less than or equal to r squared. And if I want to be really lazy, counterclockwise is like this. Wait a minute. I don't know my clocks. It's like this. Counterclockwise. Minus y dx plus x dy over x squared plus y squared. So this would be the integral from 0 to 2 pi. What's x squared plus y squared? R squared, right? What's my minus y is minus r sine t, right? What's my dx? Minus r sine t dt, yeah? And then what's my plus x, which is what? R cosine t. What's my dy? My dy is r cosine t dt. And so what do we got? Because upstairs, that numerator simplifies to what? R squared? Sine squared plus cosine squared? But sine squared plus cosine squared is 1. So the numerator simplifies to r squared. Denominator is r squared. They cancel, leaving us 1. So we just have integral of dt, which is what? 2 pi. Wait a minute. So you mean to tell me that the line integral of this vector field f is 2 pi independent of the radius? You take a circle, radius 1. You take a circle of radius 1 million. Any way you slice it, 2 pi. It's kind of neat, right? Or weird, depending on your perspective. But yes, thus, f not conservative. On where? Any set containing what? Circle of radius r, right? So if you think about that, since r can be arbitrarily small, basically it's saying if you contain the origin, right? If the origin is in the interior of your set, then this vector field is not conservative on such a set. Does this make sense to you guys? I mean, this shouldn't actually be that surprising. This vector field f, in our other way of thinking, is what? It is actually just 1 over r times theta hat. That's what this vector field is, because if you look at it, all I did was I multiplied by the square root of x squared plus y squared, what we did last time. So actually, this is 1 over the radius times theta hat. That's what the formula is in terms of polar coordinates. And so when you calculate the integral of f dot dr over a circle of radius r, well, that's the integral of 1 over, and so what is that? That's r equals to r, right? So you have 1 over r theta hat. What's dr for a circle? Well, it's r theta hat d theta. And so what you get is the integral of d theta over a circle, which is 2 pi. Again, you notice the complete lack of any parameterization there. So if you really spend some time thinking about the other coordinate systems, you can avoid a certain amount of calculation. Okay, so there's an example. There's a larger task that I should mention to you guys, which is how do we calculate the potential for a given vector field, right? How to actually calculate? How to find f such that the gradient of f is equal to f for given f, right? How do you do that? So let's suppose we have f equal to p and q for the sake of discussion. Actually, let's be three-dimensional, PQR. So you're really trying to solve this is equal to partial f partial x, right? Partial f partial y, partial f partial z. So this is a standard problem in this course, is to find little f. So that's the partial derivative of f with respect to x is p, partial derivative of f with respect to y is q, and then the z derivative, it gives you r. Now, of course, we know if you can do this, if it's possible to actually solve this, it's conservative. And if it's not, it's not, right? So we have this other list of ways to think about it, which may or may not be effective in you just saying, I'm not even going to try. I already know ahead of time it's going to fail. But another way, yet another way to think about conservative is just to try to solve these. And if it blows up in your face, that also proves it's not conservative, right? So what do I mean by that? Well, there's an algorithm. Step number 1. See, because this equality is 3 things, right? It's p is partial f partial x. It's q is partial f partial y. It's r is partial f partial z. You need to solve all 3 of these partial differential equations simultaneously, right? But these are pretty simple partial differential equations, so we have a method which is kind of ironclad. So to solve partial f partial x equals to p, what we do is integrate holding y and z fixed, right? So essentially this gives us little f of xy is equal to the integral of p partial x, you could say, plus some c1, which is a function of possibly y and z. Let me call this thing star. Step number 2, you plug star into partial f partial y equal to q, right? So keep in mind that this right here is, let me call this thing, let me give this another name. Let's call that G. Let's say G plus C1. Here, G could be a function of x, y, and z in principle, but C1 is just function of y and z by assumption. All right? So you take that, and you plug that into here. What's that give you? That gives you partial g, partial y, plus partial C1, partial y equals to q. All right? Now, keep in mind that in this process, partial g, partial y, this is a known thing. It's a specific function. Whatever it is, it is. This gives you partial c1, partial y is equal to q minus this partial g, partial y. How do you solve that? Well, you integrate both sides with respect to y, holding z fixed. Y. Right? Whatever this works out to, it gives you some function, let's call it h plus c2, which is just a function of z at most. So the constant in that integration could be a function of z. All right? So let's update what f is at this point. At this point in the process, we now have that f is equal to g, that original thing we found from integration, plus c1. But c1 we've now learned is actually h plus c2, which, by the way, is just a function of z. Let's call that star star. All right? So step 3 is we plug star star into partial f partial z equal to r. Let's see how that goes. Right? So what that's going to do is it's going to give us an equation that looks like the following. It's going to give us an equation of the form, well, we've got like partial g partial z plus partial h partial z plus partial c2 partial z equals to r. So you can solve that for partial c2 partial z is equal to r minus, gz minus hz, right? And that will tell you that c2 is the integral of r minus gz minus hz with respect to z. At which point, you put that back into star star, and you found your potential. This is a pretty stark contrast to the proof that I just failed to do, where we found a formula for f in terms of a direct line integration. Right? What's the alternative method? Or f equals to the integral from some point to x, y, z, right, of f dot dr. I mean, that's the other way you could calculate the potential for f. You could just set up the line integral from a point, a fixed point, pick a point, any point, may I recommend the origin, to an arbitrary point x, y, z, and do that line integral. I mean, you could do it that way too. Now, I think this algorithm is worthless until I give you an example. Okay, so here, specific example. Let's look at f of x, y, z equal to x plus y, y squared, z. So here's my p, here's my q, here's my r. Let's try to go through this algorithm. So to start with, we're trying to solve partial f, partial x equal to x plus y, right? Integrate with respect to x. This gives us f equals to 1/2 x squared plus xy, right? Plus c1, which is possibly a function of y and z. So an expression like I just wrote down will solve that partial f partial x is equal to my p. But we don't just have that. We have the other two things to satisfy as well, right? So that's star. This is the star I was talking about. Okay. Now, next step, we do partial, partial y of that. Is equal to what? Well, y squared, yeah? So what's that tell me? Partial y of 1/2 x squared is 0. Partial y of xy is what? It's x. And then I've got plus partial c1 partial y equal to what? Y. Yeah, y squared. But you're right. I mean, you're into the next. You have reached the next step. Partial c1 partial y is equal to y squared minus x. Yeah. But this is impossible. Why is this impossible? But if we take partial x, right, of partial c1 partial y, that would be partial x of y squared minus x, right? And you can commute the order of these. This is partial y of partial c1 partial x equal to minus 1. What is partial c1 partial x? What do I mean, actually, when I write this? What does this even mean? This is meaning partial c1 partial x is equal to 0. What I'm trying to say there is that c1 is not meaningfully a function of x. It's at most a constant function of x. So when I go into the second step in this algorithm and I find that partial c1 partial y is y squared minus x, this implicits an x dependence on c1, which is not allowed. So what does this mean? This means the algorithm fails. Therefore, this vector field is not conservative. Right? So this is a contradiction. This is 0. So we get 0 is equal to minus 1, which is, of course, a contradiction. So therefore, f such that gradient of f equal to f does not exist. In fact, if we'd calculated the curl of this vector field, we would have found what? We would have found it's non-zero. All right, so, what's the offending term here? I don't know. I need to come up, just give me a second here. Here we go. Here's a newfound vector field. This one's a little more exciting. Can you find a potential for this vector field? I mean, you need partial f, partial x is equal to yz cosine of xyz, right? So step 1, f would be the integral of yz cosine of xyz dx, so to speak, right? Which is, going to give me what? It's going to give me yz over xz. Did I do that right? Oh, I can't do math. It's going to give me yz over yz sine of xyz plus c1, which is possibly a function of y and z. Right. So, of course, the yz's cancel. So next step would be partial y of sine of xyz plus the c1, right? And that's supposed to be equal to xz cosine of xyz and so what happens here, we get we get xz cosine of xyz plus partial c1 partial y is equal to xz cosine xyz, yeah? So what happens? Well, this and that cancel, right? And we're just left with partial c1 partial y is equal to 0, which implies that c1 is equal to c2 of z alone. See, originally, c1 could have a y and z dependence. That shows it has no y dependence in a non-trivial sense. So all that's left is a possible z dependence, right? But then when you plug it into the third equation, you'll eliminate that as well. So in fact, c2 is actually just a constant in the ordinary sense of the term. So this is a safe algorithm. You integrate the first with respect to x. You plug that answer into the second, integrate with respect to y, holding z fixed. Then you take that answer and you plug it into the third, integrate with respect to z, holding nothing fixed. I guess integrate with respect to z. And after the dust settles, if you can do those 3 integrations, you found the potential. And if you get stuck along the way, you can't. All of this said, what's the best way to find the potential? Is it actually to do this substitution process, or is it to guess? I think quite clearly guessing is a vastly superior method for finding potentials for a lot of examples I give you. Like this right here, you really should be able to see, even after one integration, that f is the sine of xyz plus a constant, right? Because if you think about that formula, partial differentiation with respect to x gives you that. Partial differentiation with respect to y gives you that. Partial differentiation with respect to z gives you this. So do you need to go through this multi-step algorithm to find that f? I don't think you do. I know you don't, because I've asked you questions in previous lectures. Some of you have produced potentials for me without knowing about that algorithm, right? But you should know about this algorithm and be prepared to kind of go through it, right? Some professors have the school of thought that it's cheating to just guess and you have to go through the algorithm. That's not how I think, but I might ask you to go through the algorithm. If I want you to explicitly go through the algorithm, I will ask you to solve through successive integration or something like that is what I would say. All right. So our next big topic has to do with number 4, actually. And I'm going to show you an example rather than even the theorem. Well, I'll tell you, I'll state the theorem. Here's the theorem. The integral of p dx plus q dy over the boundary of some region R is equal